Alright, so example 3 says suppose a culture of 100 bacteria is put in a petri dish and the culture doubles every hour. Predict when the number of bacteria will reach, or will be, 250,000. Alright, so let's work on it algebraically first. So let's set up our equation. So we know it's going to be P of T equals, do we know the initial amount? Well, yeah, do we know the initial amount? 100, right? Times 1, oops, that's not a 1. 1 plus, what's my rate? Yeah, it's doubling, so it's 100%, right?
Yeah.
So it's plus another 1. That's how they get the 2, just so you know. To the T. So our equation,
100 times 2.
now, what else do we know in this? What is that 250,000? That's my ending amount, right? That's my P of T. And it says predict when. So we're trying to solve for T, aren't we? All right, so let's go ahead and plug the 250,000 in. And how am I going to solve for T? Where's it at first? It's in the exponent with the 2 as the base, right? So I need to get that by itself. How? Divide by 100. So what's that, 2,500? Equals 2 to the T. How do we get T out of the exponent? If we knew what the T root would be, you would be correct. Okay, so to get a variable out of the exponent, guys, you got to get the exponent and the base by itself, and then you're going to log both sides. Now, it doesn't matter if you use a natural log or if you use a common log, okay? Either one works. So let's use the natural log. So I'm not going to write it there actually. I'm going to natural log both sides. So we get this natural log of 2,500 equals the natural log of 2 to the T. Now, it doesn't really look like it helped me any, does it? My T is still in the exponent, isn't it? But with logarithms, we have this rule that if you have this exponent, it can bounce back to be the coefficient in front of its log. Or vice versa. If I had a number in front of the log, I can make it bounce as an exponent, okay? So, because we logged both sides, or because we logged this side, but what you do to one, you do to the other, now I can rewrite this as a natural log of 2,500 equals that T is going to bounce in front of its log, so T times the natural log of 2. And then we're going to solve for T, so what do I need to get rid of? The natural log of 2, right? So we're going to divide by it. Now, natural log is like absolute value or something like that. It doesn't cancel, okay? So you can't say because you have a natural log on top and natural log on bottom, your natural logs are gone. You can't do that. But what you can do is you can type that in your calculator. Just when you hit the natural log button, it's going to open a parenthesis. So make sure at the end of the 2,500, you close the parenthesis before you do the natural log of the 2. All right? So let's type that in and let's see what we get.
What's the natural log of log? Or like, do you do...
All right, so we put this in our calculator and we got 11.287 what? Hours. Yeah, we should always round to 3 decimal places. But I mean, like if it's people or something like that, or objects where you can't have a piece of one, then you round. But otherwise, 3 decimal places, unless it tells me otherwise. Oh, is it 288? I'm sorry. All right, so to solve graphically. Guys, you can go back to where we wrote out the equation right here. We said our equation was what? 250,000 equals, what was it? 100 times 2 to the x. And we can put this in our calculator, just like we did on 18C on that previous homework. So let's put one of them in y1. Let's put the other one in y2. And let's go look at the graph and find the intersection. Alright, so we graph it. We use the information we knew to figure out our window. And we're going to go find that intersection. So you do your second calc intersect. Enter. And you get 11.288, comma 250,000. And so from there we can see we were solving for t, which is the number of hours, which is our x. So we can see that t is approximately that 11.288 hours using our graph.